It's fine.
So thank you everyone for attending. It's a great pleasure to have with us, even remotely, Stéphane Basa. Stéphane is a research director at the Laboratoire d'Astrophysics de Marseille in France. And he has a strong experience coming from high energy physics to astrophysics, and he has a lot of experience in actually studying the transient sky and higher redshifts. And he's an expert actually in development of astronomical instrumentation. He's co-PI of the space mission SVOM. He will talk to us about this today. And also he's the PI of a robotic telescope, which is called Colibri, and it is related to that mission. And it's a telescope that has been built by France, and it's located in Mexico. And actually it's very similar to the telescope we have here in Skinakes. So it would be great if Stéphane could visit us and see our facility as well. So moreover, Stéphane is the coordinator of the Opticon RadioNet pilot. That's how I get to meet him, which is the largest infrastructure project in astrophysics right now in Europe. It's a very big collaboration of very many 30-something institutes and very large budget, and Stéphane is coordinated that and shapes the future of European astronomy. So without further ado, Stéphane.
Okay, thank you, Vasilis, for the invitation, even it is virtual. Unfortunately, I cannot be physically with you due to a personal problem, but I have promised to Vasilis to visit you soon. Not this summer, probably it's too hot for me, but in September, October, it could be very nice. So I will give you a general talk on the gamma burst on the Sino-French SVOM mission, which is dedicated to these objects. It's a very general presentation, so if you're an expert on gamma burst, I'm not sure you will learn a lot of things, except maybe on SVOM. Or even David should know everything on SVOM already. So it's a very general presentation. I just want to start with something. I'm fighting. No. Up. Voilà. I'm fighting with my screen. Just to remind you something which is obvious, it concerns the gamma rays. It must be clear for everyone that the Earth's atmosphere is not transparent to the gamma rays. Here, you have as a function of the wavelength. You should see the mouse. Vasilis, it's okay for the mouse?
Yes, we can.
Yeah. Thank you. It's more convenient like this. You have the transparency of the Earth's atmosphere as a function of the wavelength. Obviously, it's transparent in the visible domain, also in radio, but in gamma rays, the Earth's atmosphere is not transparent. It means technically that if you want to observe the universe in the gamma ray domain, you need a satellite. It's absolutely fundamental to understand this. It explains also the time scale of the discovery that I will give you later. Because a satellite is easy to say. It's easy to say that we need a satellite, but the satellite development is very long, very expensive, and sometimes risky. So I will start with maybe it could be the conclusion, in fact. But what is a gamma ray burst? I want to present this slide before to be clear, and I will go in much more detail later. A gamma ray burst is a short-lived burst of gamma ray photons coming from the universe. What means short? It means from a few milliseconds to several minutes. And what is very important to note is that it shines hundreds of times brighter than a typical supernovae. Just to be very clear, on the side, this is the sky in the gamma ray domain. Here, this is our galaxy. And when you have a gamma burst, here you will see the arrival of the photons as a function of time. You can see that the gamma burst is really the brightest object in the universe in the gamma ray domain. So an important challenge will be, you will understand quickly, the distance in this story, because it's very bright. If this object is close, okay, it's one thing, but if this object is at cosmological distance, it means that this is the most energetic event in the universe. So how this object has been discovered? So I want to make a small stop here because it's very interesting and funny, and for the youngest one, it's very interesting to know. In fact, the gamma burst has been discovered by accident. In the early 16, the United States have begun to launch a series of top-surface satellites, which has been especially designed to look for gamma rays. And these gamma rays are coming from the nuclear bomb test. The idea was to, at that time, several countries have signed a treaty, and this treaty bans the test of nuclear bombs in the atmosphere, in water, and in outer space, which is also important. In fact, I've realized this morning that France has never signed this treaty. Well, no comment. And it was interesting because at the end of the 16, these satellites, named Vela, you can see here two, they have been launched after they are split, and two, of course. In the late of the 16, in 67, in fact, to be precise, they have detected a burst of gamma rays. And it was possible to measure, at least to localize their position by measuring the time delay between the arrival of the signal between the different satellites. And they have realized that this burst is coming from outer space, not from the Earth or even the Moon. They have thought that the Russian has done some tests outside in the Moon, but it's not the case. As it is top-surface satellite, this discovery has been announced in 73. And here, it's an historical picture, because here, this is the time arrival of the burst of the photons of the first gamma burst ever detected. Alors, this discovery has been announced in 73, and during almost 20 years, there was nothing. And we have to wait for the launch of the Compton Gamma Ray Observatory by NASA. Here you have a nice picture of the CGRO satellite. It was a very massive satellite, and it has been deployed by the space shuttle. You can see the arm of the space shuttle at that time. There was several instruments on board, Egret, Compton, for example. And in the 8 corners, one here and one below, in fact, it's really on each side, there was 8 detectors to observe, to detect the gamma ray burst. On the sensor, the instrument, it was named BATSI. And it was possible to localize the gamma burst with an accuracy of about 1 degree. To localize is quite easy. You measure the time difference of the arrival of the signal on each of your corner. Alors, it's accurate or not so accurate, because in 1 degree, if you want, for example, to detect or to observe an optical counterpart, for sure, you put your simple telescope here. In 1 degree, you can find many sources. Anyway, what is important is that they have been able to detect about 1 gamma burst per day. CGRO on BATSI has been operated for almost 10 years. So with CGRO on BATSI, it was possible to have a large statistic with several thousands of gamma bursts. And with this satellite, it was possible to have a better understanding of the phenomena. Now, the first point is that all the gamma bursts are unique. We have never found 2 gamma bursts identical. Here, this is a higher voltage, insist on the number of photons detected by BATSI. And what is interesting here, you can note the duration of the event. Some are very short, less than 1 second. Here it's 1 second, so it's shorter than 1 second. Some are very long. For example, here it's 1 minute. Here you have almost 3 minutes. You can notice some spike. And also, we have never seen a gamma burst flashing again. So this event is unique. So it's probably the first hint that is associated to something which is probably explosive. An important information given by BATSI is this one. We are observing, in fact, 2 families of gamma bursts. Here you have the duration of the event. This is what we call technically the T90. It's the duration in which you observe 90% of the photons. And you can see the 2 distributions. One peak, about 10 seconds, going to many minutes. And the second peak here, what we call now short burst, and here this is a long burst. So here we have the short gamma burst, and here the long gamma burst. Something, here we split at about 2 seconds. Here you have an indication that you have two origins in the gamma ray burst. You have no explanation, but you have an indication. It's the first hint. It is also interesting to note that the spectra of these events are different. The short bursts have a hard spectrum, and the long has a soft spectrum. I can show you here the spectra of the long gamma ray burst, for example. You can see the typical spectrum of a gamma ray burst, now of a long gamma ray burst. If you multiply by e to the 2, we can observe a peak. And the peak is always comprised between 100 keV and 1 MeV, typically. What is interesting also here that you observe a power law, which is the standard signature of a synchrotron emission. The synchrotron emission is very well known in astronomy. It happens typically when you have an electron in an intense magnetic field. And what is also important for synchrotron emission is that you should observe a signal in the visible, in the gamma ray, in the X-ray, in the visible domain, infrared, of course, and radio, and so on. And here you can see that I don't give an upper limit. You will understand later why I put no upper limit now. Something also very important concerning BATSI, it was a gamma ray burst distribution on the sky. Here, this is a distribution also in the sky. The galaxy is here. So if the gamma ray bursts are coming from the galaxy, were coming from the Milky Way, you should expect to have a very important density here. I expect to observe almost no gamma ray burst at the top. Here, what you're observing is that you have an even distribution across the sky. So it's an indirect indication that the gamma bursts are coming from outside the galaxy. It's not a direct indication. You don't have a redshift, not yet. But it's a first indication that it's coming from outside the Milky Way. And I insist on the fact that it's a fundamental information, because if this object is coming from outside the Milky Way, it means that this object is very, very energetic. And in fact, we have solved the issue about now 25 years ago, a few days. And it was a very nice observation done by the BepoSAX satellite, which was an Italian-Dutch satellite. On board, there was a gamma ray burst detector. And they have, in the 28th of February, they have observed an alert in their sensor. And they have been able to slew the satellite to this position. This is very interesting to understand this. To observe the gamma burst, you need to observe a large field of view because they are coming from everywhere in the sky. And here, the consequences of this is that you have a poor localization accuracy of the gamma burst. And the trick of the Italian was to slew the satellite to this position and to observe with an X-ray telescope, sorry. And with this X-ray telescope, which has a narrow field of view, it was possible to have a much better localization accuracy. And this is exactly what they have done in February. It took about 9 hours or 9 or 10 hours to slew the satellite. It was not automatic, it was done by hand. And they have observed here an X-ray afterglow, what we call. This is the X-ray signal, the gamma burst, the 28th of February. And 3 days later, you see that the source has faded. And later, it was possible to detect an underlying galaxy, and the redshift is 0.7. It's a very strong indication that the gamma bursts are cosmological. It's not exactly it, but because we have no guarantee that you're observing the real galaxy. And in fact, a few months later, still in 1997, still by BepoSAX, it was possible to do exactly the same exercise to slew the satellite to the gamma ray burst alert, but it was very fast in 1 hour. And they have done a nice, also, it was possible also to set up some observations with optical telescope. And they have it has been possible to acquire a spectrum, sorry. And you can see some absorption line. And here you have a direct confirmation of the distance of the gamma burst, still 0.8. So it's definitively cosmological. I insist, this strategy is very important. We observe a large field of view with a poor localization accuracy, and then when you have an alert, you slew your satellite to refine the position. You will see on Swift and later SVOM are doing exactly the same thing. And now, clearly the debate is closed. Gamma bursts occur on cosmological distance. Here you have a redshift distribution. The most distant gamma burst is at 9.4, I will show you later. And you have here the redshift distribution. The median redshift is about 2. It's about 2 for the long gamma burst. For the short gamma burst, the median redshift is smaller. It's about 0.8. It has consequences, and I will come back on this later, if I don't forget, please. Or you remind me later. So clearly, when you know the energy that we receive on the satellite, and we know the distance, the gamma bursts are among the most energetic events in the universe. It's a very nice object. Now I will try to fix some ideas. Here you can find, for example, the gamma burst compared to supernova rates. Here, this is the number of gamma bursts that you expect every day in the universe. This is not the rate that you can detect, which is another story. This is what we expect typically in the universe, at the scale of the universe. We expect between 100 and 1,000 gamma bursts per day. It's large, but not so large. It's about 1,000 less than for the supernovae. Something important also, this is the energy, which is released, is between 10 to the 51, 52 erg. It's almost the same energy than for the supernovae, but the difference is that for the supernovae, you release energy in several weeks. Here, you release most of the energy in few seconds, few minutes. It depends on the gamma burst. So it's why the gamma burst is so energetic. So now, what is important is what is the progenitor, what is the origin of these events? Previously, I've spoken about the short gamma burst and the long gamma burst. Now we are convinced that we have two different origins. And after, we have a similar phenomena. I will explain to you, of course. The long gamma bursts are associated to the collapse of very massive star, or some specific one. So typically, this massive star must have a mass larger than 20, 30 solar masses. They explode. They form a black hole. You have a torus and a jet. The key is a jet. I insist on this. And to form a jet is not so easy. You need a specific magnetic field and also a specific rotation speed of the star. And for the short gamma bursts, they are produced by the collapse, the merging of two neutron stars or a neutron star and a black hole. And this event should be associated to gravitational wave signal. Here you have an image. The two stars are going closer and closer, and they're going closer and closer because they are releasing energy of the system through the gravitational wave. You have a collapse, merging. Also, again, you have a black hole, formation of a torus on the jet. And also here, what is important that for the long gamma burst, you expect to observe a supernova. So for the short gamma burst, you should expect to detect a gravitational wave signal. And this is what we have observed, in fact, but I will come back on this. The gamma burst light curve has two components, in fact. You have here for the long gamma burst and here for the short gamma burst. No gamma burst is identical. So I cannot provide you a canonical light curve. Unfortunately, I cannot. But I can give you some trend. So we have typically what we call the prompt emission, which is observed in gamma ray domain. This is the signal that we observe. In fact, this is a signal observed by Vela, observed by BATSI, by POSAX. And this is the signal which is used to trigger the satellite. And here, so it's long for the long gamma burst and short for the short gamma burst. And after we have a decay of the light curve. And this is what we call early afterglow. And it is afterglow is observed in the X-ray domain, the optical and radio. This is what, when I speak about synchrotron emission, it's typical of synchrotron emission. How we can produce this? It's always so the mechanism is almost the same for the short and long gamma burst. So I have my black hole produced by the collapse of two neutron stars, for example, or the collapse of a very massive star, 20, 30 solar masses. I have a jet, I have some matter around. So I have first the prompt emission. The prompt emission happens in the jet because in the jet you have different shell, and each shell has a different speed. And you can have some collision inside between the shells. And this is this collision which are producing the gamma ray emission. And after the jet is entering in collision with the ambient medium. And here I have the synchrotron emission. And the synchrotron emissions produce gamma ray, also X-ray, visible light, radio, and so on. And this is what we call the afterglow. So clearly, the gamma bursts are by nature multi-wavelengths because we can observe them from gamma ray, but we need also X-ray to observe them, visible domain, radio, infrared, and so on. So they are really multi-wavelengths. The time variability, I insist, is from seconds to minutes. And the lifetime is only few days. After few days, you cannot see something. So it's very short. So well, I'm here to make you dreaming. So I just want to give you some important message. I want also to trigger your interest on this subject, and clearly. So during few minutes, gamma ray bursts are the most luminous source in the universe, clearly. And you will see we can use them to as unique probes to understand the phenomena taking place in extreme conditions. Because we have jets. Jets are common in astrophysics. We have we have typically jets for the tidal disruption event, around the AGNs and so on. And also, it's a very powerful tool to study the early universe. Personally, I'm not really interested to understand the phenomena, for curiosity, of course, but it's a very nice probe to study the early universe. You will see later. But first, I would like to make a small stop on the Niels-Gerais Swift Satellite Observatory, I have to say. Niels-Gerais was the former PI of Swift. And Niels passed away several years ago. It was a very brilliant scientist. Here you have an image of Swift. And here you have the burst alert telescope. And it observes a large field of view. When you have an alert, the powerful of Swift is that the satellite flew automatically to this position, and they observe with an X-ray telescope, XRT, and ultraviolet optical telescope. Here. Everything is automatic. The philosophy of BEPOSAC has been implemented in on the payload. I want to make a small stop, I insist, on Swift. This satellite has been launched many years ago now, but almost 20 years ago. It's still in operation. We still receive alert from Swift. I have received one, I don't know, 4 hours ago. It was a very, very successful mission. Alors, in particular, because it was a cheap, but cheap double coat satellite, not very expensive compared to the other satellite, but the scientific output of Swift are very impressive. So it's why NASA has top ranking Swift among its astronomical satellite during many years. If you remove, of course, Hubble Space Telescope on GBW now on the Chandra X-ray Observatory. So it has been really a very successful mission. And I just want to say that this sentence, and to read this sentence from the NASA senior review, Swift is a premier facility for multi-wavelength time domain astronomy in the world. And I insist, it has been very successful. Just to demonstrate this, I just want to show a list. In fact, I have stopped the list after 2015 because the page is too small. Otherwise, it would be the text would have been too small. But Swift has really changed the game. And here you can see some major discoveries done by Swift. For example, I will come on this, but they have discovered very high redshift gamma burst. They have observed, for example, the first type 2 disruption event flare. They have been able to observe the first evidence for kilonova emission in short gamma burst. I will come on this later, and so on. So it's a very successful mission. Compared to the price, it's very nice. Not sure that all these satellites are at the same level, but it's a private comment. So what has been possible with Swift, in fact, now we have a clear connection between long gamma bursts and supernovae. I explained before, the long gamma bursts are produced by the collapse of very massive stars. So you expect to observe a supernovae with a long gamma burst. So we have detected about 50 core collapse supernovae since the beginning, since the story of the gamma burst. You can see here the light curve of typical what we observe usually. You have the typical light curve in R, I, and Z for gamma burst. I've forgotten to explain to you the naming of the gamma burst. Well, it's the same story than for the supernovae. You have the gamma burst, so the name, the year, the month, and the day. So this one has been observed in August 31, the 31 of August. And E is for the first of the year, of the day, B the second of the day, and C on third of the day, and so on. So for this gamma burst, you can see the light curve as a function of time. And after 1 week, typically, you observe a bump. This bump is the brightness of the supernovae, which is below the light curve of the gamma burst. So here it's a very clear signal. And here you can see different light curve for different gamma burst. And it has been possible to acquire some spectrum of these supernovae, and it is always associated to a supernova of type 1b or 1c. 1b and 1c, just to remind you, that it's associated to the massive star. So it's a clear indication that the gamma bursts are associated to the most massive star. In fact, we don't detect, it's difficult to detect the supernovae associated to gamma burst. It doesn't mean that it doesn't exist, but the detection is very difficult because the gamma burst is very bright, and in fact, the supernovae is very faint. And you can see here at redshift 0.8, it's very difficult to observe something, to confirm the supernovae. It doesn't mean that I insist, doesn't mean that the supernova is not here, but the supernova is too faint to be detected. And now we have detected very high redshift gamma burst. So this one, 090429b, so second of the day. You can see a nice picture, but it's not very impressive, in fact. But this is a small red dot at redshift 9.4, and you see the age of the universe as time is 500 million years. And what is interesting here is that you can use the gamma burst to probe the universe, because it's a very bright object. So you can observe all the matter which is between you and the object. And this is what we have done. For example, it's a very nice probe to study the reionization era. It's not the perfect probe, and we can discuss this later, but because it's not a perfect probe because gamma bursts are rare. So we don't have so many. But when we have it, it's very nice. Because, for example, here for gamma burst, this one at redshift 6.3, it has been possible to acquire a spectrum, a high resolution spectrum, and you can observe the matter between you and the object. And in particular, this is the case here. You can see calcium, aluminum here. It's not. It's a matter between you and the object. And also by observing the wing, the damping wing here of the Lyman alpha here, you can estimate the reionization of the universe, because the shape is associated by measuring the shape, how the damping is done. You can measure the quantity of neutral hydrogen at that time. And this is what was done here, for example. So here you can see you have the CMB of the Planck measurement. We can come, David is really an expert, I think so. And you can see the damping, which has the neutral fraction of nitrogen, which has been measured by the different gamma bursts here. But it follows also the Lyman galaxy. So you can see the ionization is ended at redshift 6, and it starts at 7 or 8, something like that. So something also interesting concerns the invisible galaxies, because I will make a very stupid remark, but where there is a gamma burst, there is also a galaxy by definition, because a gamma burst is not in the air like this. So if you observe a gamma burst, you should expect to observe a galaxy below. This is what has been done here. It is the first detection of the high redshift gamma burst of the Earth galaxy at redshift larger than 5. This one is not yet clear. But the two first is clear, we have a detection, but this one, there is still some intensive debate. Well, probably, I'm sure the GWST will go check this. It's a very difficult exercise, but I will come to this later on. There is, of course, the bias related to properties of the Earth galaxy. I will give you just a slide after. But what is also interesting here, that like this, you can measure the star formation rate on the faintest galaxy. Here, this is a simple simulation on Theseus. Theseus is proposed to ESA presently. I hope it will be selected. I sincerely hope. But this is typically the star formation rate that you could measure with Theseus. This is the standard one, gamma burst, corrected star formation rate, the one measured with the gamma burst. I make a stop here. I just want to remind you that the peak of the star formation rate is at redshift 2. And as the gamma bursts are associated to the most massive star, the lifetime of massive star is very short. So it's normal that the peak of formation of detection of gamma bursts is at redshift 2, because it is a peak of formation of star in the universe. I can give you some details on the Earth galaxy properties also. It's interesting because the long gamma bursts and short gamma bursts are two different origins. We have two different progenitors. So we don't expect to have the same properties of the Earth galaxy. And this is what we observe in fact. So the long gamma bursts are observed typically in star forming on young stellar population of dwarf galaxies. So small galaxies, star forming, normal. This is what I've said previously. And we have some suggestion, it's not yet clear, but probably they seem to appear in low metallicity galaxy. And it could be interesting to note, I insist on this, that it could be an unbiased pressure of the star formation and metallicity history of the universe. I just want to show this picture. It's not so impressive, but what is important here, that here the idea is to detect the Earth galaxy of the highest gamma burst. And you can see that on most of these gamma bursts, we don't detect the Earth galaxy. It's normal, it's dwarf galaxies. So the exercise is very, very difficult. Personally, I spent, I don't know, 40 hours with the VLT, not a small telescope, to detect the Earth galaxy. And I have a very nice measurement of the sky. So I have detected nothing. So it's a very difficult exercise. Well, so I'm here for that. Concerning the short gamma burst, they are expected, and they are detected in any type of galaxy, but always associated with an old stellar population. And in fact, it's absolutely normal, because I remind you that the short gamma bursts are produced by the merging of two neutron stars. And you need time to form this neutron star system, and you need also time in order that the system, in order to have the merging, because you need to release the energy by gravitational wave. So it takes a lot of time. So it explains also why the short gamma bursts are observed with a median redshift of about 0.8. Alors, something new, I want to show you some exciting results also. In fact, in the universe, monsters exist. We got the demonstration of 6 months ago. It was in October last year. A Sunday, of course, because the most important observation I always observe Sunday or the 25th of December or 31 of December, of course, when it is absolutely not convenient for your personal life, but that's like this. On this day, on Sunday 9th of October, we have observed 5,000 photons of a very high energy between 0.5 and about 20 TeV. And it has been observed by LASSO here. It is in Tibet, in China. It has been very surprising, in fact. And the Russian claim to have detected also a very high, in this case, very, very high energical photon, 251 TeV. There is some doubt concerning this detection. What is important is that this object is very close, in fact, reaches 0.1. It has triggered a very impressive campaign of observation. 70 satellites has observed more than, and we have received about 150 observation reports. So it's very impressive. It's not the record. I will give you the record in a few minutes. And so this event is incredible energical. You can see here the rate compared to the main compared to the flux, the brilliance. And it's 1 per 10 millennium. So it's a very, very rare event. Now, in fact, it's very understanding this observation is not so easy, because you have to know that the high energical photons are observed by the infrared background. And for example, for the 250 or 200 TeV photons, they are even absorbed by the CMB itself. So these photons are not coming from the gamma burst itself. So one possibility that these photons are secondary particles. They are the result of the interaction of gamma ray, cosmic rays produced by this gamma ray burst. And these cosmic rays have interacted with the ambient infrared background of CMB for the one observed by the Russian. And it is this interaction which has produced the photon that we are observing. There is still a lot of debate on this observation. And I cannot avoid this, of course, because it's very important. Now, because there is a detection of the gravitational wave by 2017. It was a major observation, I insist. It's really a major observation because it is in absolute the most observed astronomical object in history. And it is the first observation. This is the observation of gravitational alert. This is the observation of the optical counterpart for gravitational wave. Putting my sentence in the good order. And it is produced by the collision of 2 neutron stars. You can here see the signal from LIGO. Here, this is the one from Virgo is less obvious, so I prefer to present this. And here, this is a signal, the gamma burst signal, which has been observed by Fermi, which is a high energy satellite in operation since 10 years from now. I think it's I think more, 15 years probably. And also it has been observed by Integral. It's an old satellite also. Integral is less obvious, but you see a small peak. But Fermi is very clear. And after Swift, I've confirmed the observation. And it is the first association, the first clear observation of what is the source of the gravitational wave that we are observing. I show you the movie. You can see the kilonova. We come this just after. So it was a very nice observation. I insist the most observed astronomical object in history. But of course, for the Nobel Prize, it's too late now. And what we have learned from this gravitational wave observation, we have discovered, we have the clear confirmation of what we call now kilonova. Now, what is a kilonova? In astronomy, you know, we have one model, but we have only exceptions. So a kilonova is between a nova and a supernovae. Now here you have a view of what is a kilonova. Here you have the black hole formed by the collapse, by the merging of the two neutron stars. You have a tidal ejecta here, which emits in the red. Then you have your jet. The jet is enter in collision with the matter which has been ejected before by the progenitor. It produces what we call the blue kilonova. The lifetime of the blue kilonova is just 1 or 2 days. The lifetime of the red kilonova is larger, several weeks. It's quite short. Then a cocoon is formed by the matter which is expelled by the jet. And after, you have your prompt emission, which is of the gamma burst, and after the afterglow. I've forgotten to say something. I'm very sorry. That to detect a gamma burst, to see the gamma burst, your eye must be in front of the jet. If you imagine that the Earth is here, you don't see any gamma burst because you are not in the line of sight of the jet. It's something also fundamental. So now, since in 25 years, we have done a lot of progress, but we still have a mini question to address on the gamma burst, on how we can use the gamma burst to probe the early universe. We still have to understand the diversity and unity of gamma burst. Mechanism inside the jet is still complex. I've explained to you with hand, but when you go in details, it's not so clear. In fact, the connection, the gamma burst supernovae and hypernovae, connection between gamma burst and kilonova, still to be understood. In cosmology, we still need more gamma burst, and in particular high redshift gamma burst, to study the matter between you and the object by studying the absorption system that we can have. It's interesting to study the host galaxy, which has, I insist, it's fine galaxies, and it's not so easy to catch, to try the star formation rate and so on. Now I can continue. And this is exactly the motivation of SVOM, of this satellite. The SVOM has been the first meeting we got on SVOM. It was in 2005. We were 3. There was Jacques Paul. Now Jacques is retired. It was a CA, and Bertrand Cordier and me. We were only 3. It took 20 years. So when I say that having a satellite is easy, it's not so easy, in fact. The payload is this one. You can have an image. So we have Eclair. I'll give you much more details here, but Eclair is here to monitor large field of view. We have the GRM, which are also monitoring the large field of view to measure what we call the EPIC, the maximum energy of the gamma burst. And after, we have several narrow field of view instruments. One is the visible and one is the X-ray. And we have also, this is for the first time, a set of ground telescopes, the GWAC, wide angle camera, and what we call the ground follow-up telescope, CF. So it's a Chinese-French mission. So it's a Sino-French mission. So C is Chinese GFT, IF and GFT. How we will operate the satellite? So we wait for a long time. We observe with Eclair for several days. When you have an alert, automatically the satellite flew on the position, and it is done by Swift, and as it was done not automatically but by hand by Bepossax, but the philosophy is exactly the same. We send the information, we send the alert automatically to the ground, so VHF network, and we send it to the Fine Science Center, and we trigger some telescope. So of course, this telescope, we don't use this kind of telescope. They are slightly more expensive, of course, but this is a vision of my colleagues. And we send the information and we trigger automatically this telescope, this ground follow-up telescope, and this alert is public. On this end, so the GCN, so with the standard protocol VO event. So it is inside SVOM, this. And the idea, of course, is to trigger largest telescopes. Just after, VLT, ALMA. No, VLR. I have to put ALMA. This is a French radio telescope. And for my colleague for Carl, it's much better. And also, we want to trigger other satellites. So it is exactly the same philosophy than for Euclid, for Swift and for Bepossac. I insist on this point. I give you more details, but I don't want to go into too much detail, except if you are interested. But what is important here that the field of view covered by ECLAIR, so ECLAIR is developed by France, by CNES, IRAP in Toulouse, here in Paris, EPC also in Paris. What is important is that we cover the field of view of 2 radian, so it's very large, and we are sensitive between 4 keV and 150 keV. This 4 keV is very important to detect the right redshift gamma burst, because even if every photon is sensitive to the redshift, to the expansion of the universe. So here, this is a good method to detect high redshift. And here, the localization accuracy is not so good because it's 12 arc-minute, but in radius, so 24 arc-minute, the diameter. And the trigger rate is about between 60 and 70 gamma bursts per year. We have also the gamma ray monitor developed by China in Beijing. And here, the advantage is that we can measure the maximum energy, which is very important information. We can measure the energy up to 5 MeV. And then we have the 2 narrow field of view instruments, the X-ray telescope, and MXT developed by CNES and CA, of course, University of Leicester, and the Max Planck in Munich. And the MXT is here to refine the position, because when we observe with the MXT, we have a localization accuracy better than 13 arc-second in radius. So typically 20 arc-second, which is much better. And here you can then observe with the visible telescope, the visible domain. And this one is developed by China, UoC in Beijing, and this one in Xi'an, the center of China. It's a 40 centimeter telescope. We have 2 cameras, we have 2 bands, but it's 2 large field of view, 2 large bands, a blue band and a red band. We don't have any filter wheel. I really want to show this image because I spent, and Bertrand also, almost 20 years on this project. It was not easy, believe me. Sometimes we have seen the light, we have seen the death, believe me. And here, this is a flight model of ECLAIR. Here, the flight model of MXT, the 2 French instruments. You cannot see me because I have the camera in hand, but believe me, it's very nice to see this. Here, this is ECLAIR and MXT inside the container in China, the demonstration. It's not written in French, it's written in Chinese. And I received this image 2 days ago. ECLAIR is mounted, you can see here, ECLAIR, this one, is mounted now on the payload of the satellite. And MXT will be mounted soon. So we're progressing. I can show you also the VT, a visible telescope, the Chinese telescope. And now we expect to launch the satellite in March next year, March 2024. So, almost 20 years. It was very long. I show you also the French follow-up telescope. It's my baby. This telescope is presently at OHP, Observatoire de Provence in France, but it will be dismounted in June. And the departure date is now fixed to the 23rd of June. It's a brand new telescope, especially designed for SVOM and more generally on the transient sky. It's a very fast telescope, I will show you. It's a 1.3 meter telescope. We have done a huge effort for the image quality to protect the signal to noise. And we have a very nice image quality now. And the telescope will be seeing limited, of course. I don't have, but I have to be reasonable. And the thing, and this telescope would be installed in Baja California, in Mexico. And the median thing is 0.8 arc-second. So we will have a very powerful telescope especially designed for the transition sky, and SVOM in particular. Because we have also it's an Smith telescope. We can have two instruments. The first one will be an imager with a field of view of 26 arc-minute. And we are very proud because even in the corners, the stars are very nice, almost perfect. And we are covering from the B band to Z band. And we have also an infrared camera observing up to H band. So we have 3 simultaneous cameras, in fact. Just a demonstration, you can see the telescope in operation. It was 2 years ago when we have installed it at OHP. In fact, we have installed the telescope at the time of the COVID, which was very nice, a very good idea. I'll let you imagine why. And what is impressive with this telescope is that it's very fast, and you can start your observation about in less than 1 second after your arrival on the position. And it's very accurate, very precise. But we have collaborated, but we want to expand the SVOM follow-up network, of course. It's one of my duties, in fact. So we have also already some official partner. We have also some associate partner. We plan also to buy some observing time on some facilities. And I show you this to trigger your interest, of course, because everybody is welcome to contribute to this follow-up network. I'm reaching the end of my talk. Just the 2 last slides, just a small comparison between SVOM and Swift. So SVOM has been designed to be the successor of Swift, clearly. So we are more sensitive below 20 keV than Swift. So we are more sensitive to the high redshift gamma ray burst. We have the possibility to measure the peak. And we have done very nice, very important effort to have a multi-wavelength coverage from visible to MEV. For the afterglow, we are more sensitive also. So we are also possible to observe in the visible domain. And also we have done a special effort on the observing strategy. Because when we have a gamma ray burst, it's during the night. So it's almost equatorial. So it's much easy to trigger the largest telescope. And also, it was not the case for Swift, however, we have really dedicated follow-up robotic telescope associated, which has been designed, built especially for SVOM. I just want to say that the most exciting can be something else, in fact, because SVOM will be launched next year, in less than 1 year now, at the time of FLA 60, of SCAR, CTA, KM3. So what we will find with these new facilities, I don't know yet. You can imagine, but SVOM has been also designed to be the natural complement of all these facilities, as it was the case of Swift. But I insist, SVOM is really timely with LA60, SCAR. I should have, I've done an error. We have also Virgo, LIGO, all the gravitational wave detector. So just to conclude, the sky is really rich in transient objects of many types. I hope to have convinced you. I'm focused on the gamma burst, but we can speak a lot of time on the typology of event, also the fast optical transient, also there's many things. It's a terra incognita, partly. So Swift is exploring the transient sky. Swift is still in operation, and it has been very successful. We have many new discoveries in time domain science, including the enthusiasm on the gamma burst. I insist, the time domain for me is just beginning. You see, I'm very enthusiastic, and SVOM is the optimum follow-up to Swift. So SVOM will now be in operation in less than 1 year. So everybody interested, students, all right, special message to student postdoc. I'm too old now to do all this analysis, so young students are welcome, and also confirmed scientists are welcome, of course. So if you're interested, please raise your attention. Thank you.
Thank you very much, Stéphane. This is a very interesting talk and yet another reason for which we should be thankful for people building high quality instruments, which makes always discoveries much easier.
Go like this, it's better.
If there are some people who have questions, please raise their hand. I think Vaso Pavlidou has probably a question.
Hello, that was a fantastic talk and a very impressive network of follow-up facilities you have lined up there. I'm really looking forward to see what's coming next. So my question is, have you foreseen anything about optopolarimetric follow-up?
You expect to have, it's a good question, because you expect to have some polarization with the gamma ray burst. It's interesting to the phenomena. In fact, it's not so easy to measure on ground, but even in space, of course. No, because in fact, I've not focused my attention on this because it's an error. No, it's a good comment. If you have a suggestion on polarization and so on, everybody is welcome.
We absolutely have suggestions on polarization. This is one of the big things we do here at SKINACA. So I'm hoping we're going to have the opportunity to have you later for an in-person visit here so we can talk about this in more detail. But let me just take this opportunity to evangelize just a tiny little bit. So
no, but I'm even more motivated to visit you now.
Exactly, that would be wonderful. So we have been running the RoboPol optopolarimeter here since 2013, very successfully at the 1.3 meter telescope at SKINACAS. And the plan is when our biggest wide field polarimeter is installed at a 1.3 meter, we're going to move RoboPol to a new telescope with a fast dome, exactly having in mind time domain science. So we have already actually, blazars is the thing we have done mostly with RoboPol, but we have followed up as a target of opportunity on occasion some gamma ray bursts. We have 2 publications on those. In one case, we did not find any polarization. We also measure field stars, so we can take out interstellar polarization and measure polarization down to very small levels, that depending on the brightness of the burst, of course. And in the second case, we did find polarization. So it's not something that we're not original and genuinely interested in. And we're very happy to be seeing this new mission coming up, and we should definitely talk. So with this, I will stop and let other people ask questions. But,
but
that's great.
I'm even more motivated because, in fact, also there is only very few measurements on polarization on the gamma burst. Liverpool telescope has done some measurement, not so many, in fact. But yes, it could be very interesting. It's a good comment.
Thank you, Andrea.
So I have a question regarding, probably you mentioned it, but I missed it. I was wondering what is the response time to the trigger from Eclair in order to get the imaging observations with the X-ray telescope and the optical telescope?
Alors, in fact, it's almost in real time. The trigger is developed by CA in Paris by the team of David.
Okay.
So he shouldn't be an expert. No, the response time is very. Alors, it's a complex story. It's not a problem. It's linked to the shape of the gamma ray burst, in fact, because it depends. For example, here for such a gamma ray burst, you can. Okay, I'm doing like that. One moment. Huh? Up. For this one, when the rising is very fast, you have the delay. We speak about milliseconds, so it's very short. After it's much more tricky, this story, because imagine it depends also, because it depends. For example, here you can trigger, for example, on the second spike. So it's why on SVOM, the colleagues at CNES has developed different kind of trigger. The standard trigger is that you trigger on the trigger rate, for example. So you apply a threshold. You have a noise here, which is a background, and you apply a threshold and you trigger. And here it can be tricky because if your threshold is too high, you can trigger the second spike, and you want to avoid this. And there is also an imagery trigger. The Eclair is building an image of what is they're observing in real time. So it's very efficient for the very faint, or for this object which are very faint below the threshold. But here the delay is longer because you need to accumulate some photons.
And how much is the slew time in order for the X-ray telescope and optical telescope to point?
I would give you the standard time. It's typically, it should be right. Maybe I can move. It's 5 minutes, you see, on the below the satellite.
Okay.
But this is what we expect. But we can have some exception because the slew is something complex of a satellite because you need to avoid the sun, for example.
Yeah.
So sometimes the travel can be longer than expected. So we expect to have something in 5 minutes.
Okay. Oh, that's pretty good. Okay.
But what is important is that as the information is received, for example, Colibri will start the observation within 1 minute after the trigger. We have 30 seconds to reach the ground and then 30 seconds to trigger the satellite. So for example, Colibri will start the observation before even the X-ray telescope.
Oh, I see. And the localization from Eclair is good enough so the whole region will be covered by the ground-based telescopes.
But in fact, we have designed. No, for me, but I don't have to say this to my colleagues, but for me, the localization accuracy is poor. 24 arc minute in diameter. It's large. Huh? It's the size of the moon.
Yeah.
But we have designed Colibri especially for this localization accuracy because it is a requirement. So we have designed the telescope for this. But now all these telescopes, for example, all these telescopes has 25, 30 arc minute field of view. It is quite standard for this kind of telescope now.
Yeah. Okay. Thank you.
David, maybe, and then Nikos.
Yeah, it's a very nice talk review. I was wondering, you said that all GRBs are unique, and you also showed the complexity of all the interactions of the shocks and everything. So, is the uniqueness of the GRBs completely understood by the fact that it's a complex system, or is there some hidden possible issue of like some physics that we still don't understand?
No, our understanding. I put a lot of caution on this because I have given to you a nice image, but when you go in details, as you know, now, in fact, for example, I have considered, but I've decided not to speak about. But now we have found we have thought that it was short gamma burst, but it is in fact a long gamma burst. It's produced by a collapse of massive star. So, everything is complex. No, in fact, it's due to the fact that the explosion, the trick is how we can produce jet. It's very complex. It's not so easy, in fact, as you know. Producing jet in astrophysics is easy to say, but in reality, it's much more complex because we have a lot of failed jet. And here, our interpretation is that here it's really explosive, catastrophic. So every gamma burst is different, in fact. This is our understanding. Really, the shock here is different. So we have no hint that we can later have a simple model. In fact, you have here the signature, David. We are not able to have a canonical light curve. You see here, for example, on some we have standard decay. Sometimes we have observed some flares. It's due to a new shock. Why? I don't know. We have observed some plateau also. Why? It's not so clear. It's interesting.
Okay, Nico?
Hello, thank you for the very nice talk. Could you go, at some point you discussed how you can probe the medium in between us and you, yes, there. So can you like rediscuss this a bit because I didn't really get it?
Ah, okay. Yes, it's long. Maybe David, don't know, but it's not so. Just to explain.
Sorry, but first of all, I'm I'm a bit confused of this spectrum, because how does it go so high at 9,000 angstrom? Is it real or is it some mask?
No, it's a real one. Here, in light gray, this is the original spectrum. A dark gray, in dark, this is an average. There have been, I think they have some 3 bins, something like that. Here, just to explain to you exactly what we're observing. Here, this is the afterglow, the light emission of the gamma burst. And you can see, the advantage of gamma burst that the spectrum of a gamma burst is uniform. It's a really power law in wavelengths. And here, what you're observing, this is absorption, the Lyman foray, Lyman alpha, sorry. Here, what is interesting here, you're observing here, in this box, this is a zoom of this part, you see?
Yes.
We have a zoom. And what is interesting here, that we can modelize what we call the damping wing. And this modelization is the mixture of the host galaxy, because you can have matter inside your host galaxy, and also intergalactic medium in red. And what is interesting here, that you can see the combination of the two. You can see that what you're observing is a combination of the absorption in the host and the intergalactic medium. And it was possible here to measure the quantity of neutral fraction of hydrogen. And I don't have I should have found a better, it's not so easy, because I should have, maybe I can, later, another talk, when I will visit you, I will bring with me the same kind of spectrum from some Lyman galaxy, and so, for example, Lyman belt galaxy. By observing the damping here, damping wing, as we call, we can measure the neutral fraction of nitrogen. So it's very interesting. The power, and what is also important, I just want to promote gamma bursts, is that the advantage of gamma bursts is that they are very bright. Really bright, much brighter than the Lyman bright galaxy. So you can have a very nice thin to noise ratio on your spectrum. So it allows you to have a nice measurement here. You see the break is very clear. On in red, this is you see the thin to noise of the spectrum. Hope to be clear?
I'm not sure, but I guess it's a bit complicated.
When you will visit us, I think Nikos will be here and you will discuss more. I don't know, Andrea, do you have another question, or is it the hand from previously?
Well, it's forgotten, but I have another question if there is time.
Yeah, let's have one last question.
Yeah, I was wondering, is there any plan for additional observations while there are no GRBs, in the same way that Swift is doing additional science?
Yes, it's missing in my slide, but yes, we have what we call general program. The first year, we're working already on the first year. And after, the first year is not open, it's not public, not yet. As always, because first year, you have all the calibration of the satellite, it's a long process, and we don't want to put a lot of pressure on the team. But the second year will be open, will be public. In fact, it will be open to almost everybody. I speak about the French time. For the Chinese time, I don't know what will happen. Right. They said that it will be open, but I suspect it will be open only to China. And they are so numerous that, believe me, they can fill the schedule easily. There's no problem. But for the French time, it's split almost in two. In fact, France has 40% of the time and China 60% of the time. This is a ratio between the budget and basically what we have put on the table on both sides. So the French time will be public. There is one condition. We are not an observatory as Integral, for example. We don't have, we cannot provide the support to an external observer. So we ask that if you want to apply to SVOM, to associate a COI, a French COI. Or if you want, you can associate the French PI or the French COPI. It's even better. French COI, because this COI will have to make the link between the observer and the SVOM. So it will be open.
Okay, thank you.
Well, thank you very much again, Stéphane, for this excellent talk and taking the time to prepare it. And really, we look forward to having you in person and discuss the science with you, as well as potential collaborations with the telescopes that we have here. Thank you very much all for the talk.
Thank you.
Thank
I'll
you.
see you
Bye.
soon,
Take
though.
care.